This is lecture 18 of Physics 210A, that is thermal physics, and we've been discussing phase transitions. So far, we have discussed first order phase transition, and let me just recap a bit. And what we saw in first order phase transition is that if I am on a phase equilibrium line on PT, then on this line the specific Gibbs energy is the same. However, if you calculate its derivatives, dG1 over dt at specific P, which is S1, the specific entropy, this is not equal to dG2 by dt P, which is S2. And similarly, dG1 over dP at constant temperature, which is specific volume, is not equal to dG2 by dt dP T, which is specific volume of V2. So, both the entropy and specific volume change across the phase transition, and the slope of the equilibrium line is given in terms of these changes, which are S2 minus S1 over T V2 minus V1. No, there is no T. And these are known as first order phase transitions. Delta S, which is S2 minus S1 not being 0, implies that there is latent heat, and the volume also changes. Now, extending this same classification scheme, one can also define higher order phase transitions, and what we are going to focus here on is the second order phase transition, and this is going to be defined or classified by what is known as Ehrenfest classification, whereby we say that across the phase transition, G1 is equal to G2, where phases are 1 and 2. Then you have the first derivative, dG1 over dP at T, equal to dG2 over dP at constant T, and this means specific volumes also remain the same. and the other derivative dg1 over dt at constant p, which is S1, is equal to S2, which is dg2 over dt p. That means the specific entropy also remains the same. So, the Gibbs energy as well as its first derivatives are the same on the phase boundary line. That's number one. But what is different for the second order phase transition is that the second order derivatives are changing across the line. Now, for second order phase transition, the second order derivatives are discontinuous. Across the phase boundary lines. So, this is known as Ehrenfest classification. So, if the second order is also continuous, third order is discontinuous, just imagine if it is, then we will call it third order phase transition. So, let us see what these derivatives are, and I do that on the next slide. So, again we have this P-T diagram, and G1 equals G2, S1 equals S2, V1 equals V2, and the second derivative, that is d G1 over dt at constant p, the second derivative, which is equal to d by dt of S1 at constant p, which by definition is Cp over T. And let me call this 1, is not equal to d2 G2 over dt square at P, which is d S2 over dt P, which is specific heat at constant pressure for the second phase. So, we are talking about phase 1 on one side and phase 2 on the other. Similarly, the second derivative with respect to pressure is not continuous. So, d2 G1 over dP square at constant temperature, which I am going to write as dV1 over dP at constant temperature, which is V1 kappa 1, is not equal to d2G2 dP square at constant T, which is dV2 over dP at constant T, which is V2 kappa 2. Since V1 equals V2 equals V, so kappa 1 and kappa 2 are not equal. So, in a second order phase transition given by Ehrenfest criterion, Cp1 is not equal to Cp2 and kappa 1 is not equal to kappa 2. So, compressibility changes and the specific heat changes across the second order phase transition. Examples of second order phase transition are: 1, when ferromagnets are heated, they turn into paramagnets. And this change occurs at something called the Curie temperature. The temperature at which this happens is known as Curie temperature. 2, when certain materials such as lead are cooled, in the absence of magnetic field. And that is important because the order of phase transition changes in and in the absence of magnetic field. They turn into a superconductor, which has certain properties. Number one, the resistance is 0, but it has more properties than just resistance being 0. It has something called the Meissner effect, in that it expels all the applied magnetic field out. And this is a second order phase transition. Again, I specify when B applied, that is, a magnetic field, is 0. In the same vein, we can say that when normal fluid and the common example is the helium is cooled, below a critical temperature, it turns into a superfluid, that is 0 viscosity. And that is also a second order phase transition. There are more subtleties to this, but we are not getting into that. I just wanted to give you these examples. So next, can we relate the slope of the phase equilibrium line to the properties that are discontinuous across the phase boundary line in the second order phase transition? And it turns out that we can, and these are known as Ehrenfest relations. For second order phase transition. The trick is exactly the same as we did for the first order phase transition and obtained Clapeyron relationships. So again, consider the PT diagram for the phase transition, and we have these 2 points, Tp and T plus dt and P plus dP. Now recall that in the first order phase transition, we calculated G at the 2 points on the 2 sides of the line, and then use the condition that G1 equals G2. So for the first order transition, we calculated change in G for the 2 phases between the 2 points shown and equated them. And this gave the Clapeyron equation. Now, here G is not continuous. What is continuous here is that S1 equals S2 on the 2 sides. That means S1 Tp on one side is equal to S2 Tp, and S1 T plus dt and P plus dP is equal to S2 T plus dt and P plus dP. Now we can expand this and write that S1 T plus partial S1 with respect to T at constant P times dt plus partial S1 over partial P at constant temperature dP is going to be equal to S2 Tp plus partial S2 by partial T P dt plus partial S2 over partial P at T dP. Now, by the condition that S1 and S2 are equal at T and P, we can cancel the first term. Partial S1 by partial T at P is by definition Cp1 over T dt plus, for the second one, ds1 by dP, I'm going to use the Maxwell relationships, and this is equal to minus dV dt at constant P dP, and this is for V1. V1 is also equal, but its derivative is going to be different. And this is equal to Cp2 over T dt minus dV2 over dt P dP. Now, dV by dt at constant P is nothing but the volume expansion coefficient times the volume, and therefore we get Cp1 over T minus V is the same in both cases. So, V1 and V2 is going to be V times beta 1 is going to be equal to Cp2 over T minus V beta 2. Oh, sorry, this is times dt times dP times dt times dP. And therefore, I get V times beta 2 minus beta 1 dP equals 1 over T Cp2 minus Cp1. And this gives me times dt. This gives me the relationship that dP over dt for the second order phase transition is going to be Cp2 minus Cp1 divided by T, beta 2 minus beta 1 times V. That's the first Ehrenfest equation. So this is what the slope is going to be. One can also derive another equation, which I am going to call the second Ehrenfest equation, by looking at that V1 at Tp equals V2 at Tp and V1 at T plus dt, P plus dP is equal to V2 at T plus dt and P plus dP. Expand the second one and you get V1 Tp plus dV1 by dt at constant pressure dt plus d V1 over dP at constant temperature dP is equal to V2 Tp plus dV1 over dt constant pressure dt plus dV2 over should be 2 dP constant temperature dP. You may wonder why I am writing V1 and V2 on both sides when they are equal. Well, they may be equal, but their derivatives are not, and therefore I have to specifically write that is the derivative with respect to T of V1 and V2. Now, by the first criteria, by the first equation, this cancels, and you end up getting, and I'm just now skipping the middle steps, that dP over dt is going to be equal to beta 2 minus beta 1 over kappa 2 minus kappa 1. So this is related to the ratio of the difference in volume expansion coefficient and the compressibility. So this is the second Ehrenfest equation. So for the second order phase transition also one can derive, and one has obtained the slope of the PT line. Now let me quickly solve an example using this. This is related to the ferromagnetic-paramagnetic transition. The problem is that the Curie temperature for nickel, for ferromagnetic to paramagnetic transition is 630 K at 1 atmosphere. If the pressure is increased to 100 atmosphere, find the change in the Curie temperature. And what you're given is, in this case, the data delta Cp is 6.7 joules per Kelvin per mole. Delta beta is given to be 5.5 times 10 raised to minus 6 per Kelvin. The density of nickel is given to be 8.91 times 10 raised to 3 kilogram per meter cubed, and its atomic weight is 58.7. So we are going to use the Ehrenfest relation, and since we are given the change in the specific heat and the volume expansion coefficient, we are going to use the first Ehrenfest equation, which says that dP dt is equal to delta Cp divided by T V delta beta. We know delta Cp, we know delta beta, we know V is 1 over the density, and so we can plug in the numbers. Now, you're given Cp is in 6.7 joules per mole. So I need to change it to per kilogram. So this is going to be 6.7 joules, and 1 mole is 58.7 times 10 raised to minus 3 kilogram. So this is going to be this many joules per kg. V is volume per kg. So this is going to be 1 over the density, and this can be written as 1 over 8.91 times 10 raised to 3 meter cubed per kg. You're given delta B, so plug in all the numbers and you get dP dt equals 6.7 times 8.91 times 10 raised to 3 divided by temperature is given to be 630 times 58.7 times 10 raised to minus 3 times delta beta, which is given to be 5.5 times 10 raised to minus 6. Now you know dP dt, so delta T is going to be dP dt inverse times delta P, and you plug in the numbers and you're going to get about 0.033 K. So even after applying this enormous pressure, one does not see much of a change in the Curie temperature. With this, let me conclude this lecture by stating that Ehrenfest criterion, or what is known as a classification, so let's use the right word, classification for phase transition has been specified for a second order phase transition. Number 2, Ehrenfest equations, 2 of them for dp dt have been derived, and finally a problem applying Ehrenfest equation 1 to find change in Curie temperature. With pressure. Has been solved. Thank you.